Hello everyone, let's look at Leetcode question 1564. Put boxes into the warehouse 1. You are given two arrays of positive integers, boxes and warehouse, representing the heights of some boxes of unit width and the heights of n rooms in a warehouse respectively. The house's rooms are labeled from 0 to n-1 from left to right, where the warehouse's I, 0 indexed, is the height of the ith room. Okay, so you're basically given boxes and a warehouse of different heights, and we need to figure out how many boxes can fit into the warehouse. The rules are that the boxes are put into the warehouse they can't be stacked, okay? You need to rearrange the insertion order of the boxes, okay? Boxes can only be pushed into the warehouse from left to right, okay? So there's no opening on the other side of the warehouse, it's just one opening. If the height of some room in the warehouse is less than the height of the box, then the box and all other boxes behind it will be stopped before that room. That makes sense because if you have a height of box, let's say 5, and in the room it's only of height 5 as well, and the box behind it is height 1, we say, okay, for sure the box 1 won't fit into the warehouse because this box of height 5 is blocking the entrance. So it's important to figure out a way that we have to organize the boxes so at most we can put in as many boxes as possible. So let's go into depth with these examples in a second, but first let's look at the constraints. So n is equal to the warehouse.length. Okay, that's one array. The range of the box's length and warehouse length is between 1 and 100,000 units. So this could be a very big warehouse and a lot of boxes. And coincidentally, no, it's Google, not Amazon. The constraints are that the box's I and warehouse's I of the box's height are between 1 and a billion. Okay, that's just ridiculous. The heights of the boxes and warehouses are 1 to a billion. Okay, let's figure out how do we solve this problem. Okay, to solve this problem, we first define I to be 0. This will represent the number of boxes placed in the warehouse. Next, we can loop through the box height in sorted reverse order for the list of boxes. So, initially we have the boxes to be of heights 4, 3, 4, 1. This turns into 4, 4, 3, 1, with the smallest in the front and the largest in the back, because remember, we want to figure out a way to place the boxes in the warehouse, maximum amount of boxes, and to accomplish this, we have to sort the boxes in reverse order. And this makes sense. If we loop then to the if condition, we check if I, the number of boxes in the warehouse, is less than the size of the warehouse, the length. This means that box can in fact enter the warehouse, and the box height is less than or equal to the warehouse at index I. This just means that the box that we're iterating through is less than or equal to the current height of the warehouse. And we increment I plus or equals 1 after placing the box into the warehouse. Notice that we only increment I if the condition is met, that the warehouse length and the box height meet the requirements. And finally, we return I. This will be the number of boxes that made it inside the warehouse, the maximum amount of boxes that fit. Okay, so in this first example, we define I to be 0. This will be the number of boxes that have been put in the warehouse. Then we can loop for all the box heights. In this array, it's 4, 3, 4, 1, and after it's sorted, it's 4, 4, 3, 1. And we check then. If I is less than or equal to the length of the warehouse, yes, I 0, and box height is less than or equal to warehouse I, let's check if this is true. Okay, so the first box is height 4, and the warehouse height initially is at index 0 of height 5. So clearly, the first box can fit into the warehouse, so we can just put it here. Notice that it's the biggest box placed in the biggest initial warehouse space. Next, we increment I by 1, and I becomes 1. We go through the iteration again, and we see that the next box of height 4 is checked if it fits into the warehouse of I. Nope, it does not. Warehouse at location 1 is too small, so we don't proceed with this if condition and go to the next iteration. We see that it is of height 3, and this in fact fits for the next location. Should be height 3 and height 3 of this. It's a little uneven, but these are the same height. One is of height 4 and the other is height 3, so they fit. And then the next iteration then, since I is incremented by 1, it's now at location 2. So I is now equal to 2. And we do the same thing. I is 2. Is that less than or equal to the length of the warehouse, which is 5? Yes. So the box height of 1 is less than or equal to the height of the warehouse at index 2, which is 3. Therefore, we can place the box in this location. Notice that we did the loop iteration with the biggest boxes to the warehouse first, even though we said that the solution would implement the smallest boxes in first. This is essentially true because if you think about the biggest boxes being placed in the initial indices, the very initial first indices, we get rid of them and slowly add the smaller indices as the warehouse progresses to greater values, more depth into the warehouse. And so when we're finished with the solution, it looks like the smallest boxes were placed first. However, the code practically and literally places the box of the biggest sizes first. Okay, let's look at this next solution. We have input boxes 1, 1, 2, 2, 3, 4, and the warehouse is size 3, 4, 1, 2. So we don't sort the warehouse size, but we sort the boxes once more in reverse order, the biggest at the beginning and the smallest at the end. So it is in reverse order. We traverse the box height and we check then. If I is less than or equal to the warehouse height, yes, I starts at 0, and the box height 4 is less than or equal to the warehouse at index 0. Okay, let's check this one. Okay, clearly the first warehouse height is 3 and the first box is height 4, so right off the bat we can't put this warehouse box into the warehouse. So we skip this iteration. I does not become incremented since this if condition is false, and we go to the next iteration of boxes. The next box height is, now it looks like 3. Yeah, 4, 3, 2, 2, 1. So we put this box. Let's check if it's the height 3 less than or equal to warehouse 3. Yes, 3 is equal to 3. Therefore, we can place this box right here. I is still less than the length of warehouse, which is 4. So we then increment I by 1. I becomes 1. And we check then if, once more, the box height, 2 it looks like is next, fits into the warehouse. So it does. Box height less than warehouse height I. True. We iterate then and I becomes 2 now, so we increment the index from warehouse 1 to 2. And the next index is of the box 3. Height 3 once more. Or height 2. Yeah, it's height 2. However, the warehouse index is 2 and it does not fit into this index I. So we simply skip over this I index. I still remains 2. However, we iterate to the last box, which is of height 1. This height 1 box goes through the rotations once more, and we see that the if condition is less than or equal to the warehouse. Yes. The box height of 1 is less than or equal to the warehouse at I. It's equal to, 1 is equal to 1. And we finally exit the box height loop since we've run out of boxes. And we can finally return I. So we ended up at 0, 1, 2 plus 1, that's 3. So 3 boxes have been returned. Okay, let's test our solution. And it looks like it works. Very nice. So what is the time complexity of this solution? So since we're using the sorted method, the time complexity of this solution is O n log n, where n is the length of the boxes list. This is because the solution involves sorting the boxes list, which has a time complexity of O n log n. Also, there's a single loop that iterates through the sorted boxes, and this is O of n time, which simplifies as O n log n. The space complexity then is solution O of 1, because we use a constant amount of extra space to store the variable I. That's it for this solution. Thank you for watching.